It's January now, and a hot drink is great on a cold day. A ring on the coffee table, not so much. So I made coasters. I wanted a design on them, which is usually done with a raised print and setting a color change in the slicer, but a bunch of crevices to clean are a bad idea, so I made it an inlay. I've seen a lot about 3D printing an inlay on the bottom, but nothing about doing one on the top surface. It turns out that works quite well. In this video, I'll gloss over prepping the SVG and importing since it's covered in a previous video. Naturally, coaster and inlay will be designed in FreeCAD. This time I'll manually join the Gcode for the coaster and the inlay in a text editor so it all prints in one shot, with a pause for a color change, of course. Since a coaster works best if it has a cork base and stackability is a plus, I'll also design templates and tools for cutting and gluing cork to the coaster. So we start with an existing SVG in Inkscape. I'm going to gloss over most of this since I've shown it before. If you would like to see the details, go to the video above. First, we see that this SVG is using a custom page size. Just to keep things consistent for FreeCAD, let's go to Document Properties and pick a standard A4 size for the page. And just like previously, we'll move the SVG itself to be centered on the upper left-hand corner of the page. And that's about it. I'll save it as hotdrinkinlay.svg and move on to FreeCAD. In this design, I want to have a square coaster with rounded corners. I've already measured my mug and decided on 110 millimeters for the length of the sides. While it is possible to add a fillet to the corners of an existing solid, I've decided in this case to do the rounding in the sketch just to make things a little easier and more stable to manipulate later. So we'll start with the sketch on the XY plane, create a square, constrain the sides to be equal, and now we're going to round the corners using the filleting tool. Now we select all of the corners and make them equal. I'll set the radius of one of the corners. I think 6.5 millimeters will do nicely. Now I'll constrain the height of the square to match my cup. Finally, I want to make the square centered on the origin. The usual trick of picking opposing corners in the square and then the origin point and making them symmetric is not going to work because the corners are gone. So I'm going to add a construction point on the horizontal line and a point on the vertical line. Now I'll select the endpoints of the horizontal line and the construction point and make them symmetric. This gets the point to the center of the line. Now I'll constrain that point to be on the y-axis. This makes the square symmetrical over the y-axis. Now we'll repeat the process on the vertical line and make the point be on the x-axis, so now the square is centered. And that's got us fully constrained, so we'll close the sketch now. I want the coaster to have a 2 mm thick base and a 3 mm high lip around the outside, so we'll extrude the sketch to a total of 5 mm. Now I'll select the top face of the shape and create a sub-object shape binder. Go into the data pane and give the shape binder an offset of -2 millimeters. That will give us our 2 mm thick lip around the outside of the coaster. Now to get our 3 millimeters of height in the lip, we extrude the shape binder to -3 millimeters and do a Boolean cut. That's our basic shape. Just to keep things straight later, let's rename the cut to base. So now we'll hide the base away to make room to work on the SVG. Import the SVG and we see our paths are looking pretty good, but there is an issue. Each path is entirely separate, so if we extrude the whole thing, the snowflake will be hidden inside the extrusion, as will the inside hole of the handle. So we're going to have to get a little more creative. First we can select the cup and the steam lines and make those a compound object. Next we'll select the cutouts in the cup and make those a second compound object. Now we can select both compounds and extrude them to negative 0.6 millimeters, the thickness of our inlay. I say negative since that will make the math a lot easier later when we combine them into the base. Now we just need to perform a Boolean cut in order to come up with our final inlay. Perfect. So with that squared away, we can bring back our base. Go into the data pane for the cut from our SVG and set a Z offset of 2 millimeters to bring it up to the surface of the coaster. This is why we use negative 0.6 millimeters for the extrusion, so that now the inlay properly goes into the base with a simple Z offset. As you can see, our inlay is just a little bit too large to fit into the coaster. To fix that, we select our cut and make a draft clone. Now we come down into the data pane for the clone and set our X and Y scaling to 0.90. That looks a lot better. Now we make a pocket for our inlay by selecting the base and the clone and doing a Boolean cut. Keep in mind that making the cut hides the clone but does not consume it. We will be bringing it back out later as the inlay when we export to the slicer. Now create the registration rings just as in the previous video. But there's a trick I picked up since then. If we make the registration rings well less than the layer height high, 0.2 millimeters in this case, they'll show up in the object view of the slicer but will not generate any Gcode as they are too small to print. No more messing around with negative spaces. We will rename the fusion of the registration ring in the cut to coaster. And now if we go into the coaster and into the cut, we can select the scaled clone of the inlay and fuse it with the other ring, giving us the inlay. Unsurprisingly, we will name that inlay. So now we just export our inlay and our coaster as step files and move on to the slicer. Now for the slicing. Because we're going to be doing a top inlay, we will be printing some of the layers out of the usual order. So there's a couple of things to take care of before we get started. First, go to Filament Settings, Filament Overrides, and set a Lift Z value of 4 millimeters. I chose 4 millimeters since the lip of the coaster is 3 millimeters high, so one more to make sure everything clears. If you want to try this with Cura, the equivalent setting is called Z-Hop. Also, because we'll be editing the resulting Gcode, let's make life easier for ourselves by going to Print Settings, Output Options, and checking the verbose Gcode option. That option causes Prusaslicer to add helpful comments to the output, so we can more easily navigate the file. With that out of the way, we can go ahead and import our inlay. The registration ring is doing double duty for us here. When you import anything into the Prusaslicer, it is dropped so that the lowest point is touching the bed. Generally, that's the right thing to do, but that would be a real problem for the inlay because we need it to start printing at 1.6 millimeters. Because the registration ring was at 0 millimeters when it was fused to the inlay, the object rests on the ring, keeping the inlay itself suspended in air where it should be. Prusa gives us a warning about the empty space between 0 and 1.6 millimeters, but proceeds under the assumption that the user may know something it doesn't, and the user is always right. It turns out the user does know something it doesn't know. The coaster will have been printed by that time, and the inlay will have a nice bed of the existing coaster to print on. Warning when something seems wrong, but continuing anyway whenever possible is the right thing, and is a sign of properly designed software. Now we go ahead and import the coaster itself, and just as in the previous video, we line up the registration rings. So now we'll switch over to the slice view, and you can see that as promised, the registration rings have not appeared in the output. They're just too short for the layer height, and in this case is a good thing. The coaster is to have a white base with a black lip on it, so as we would any time we're doing a color change, we select the coaster, find the correct level, and click on the plus sign next to the level slider and select color change. Now with the inlay hidden and the coaster visible, we export Gcode for the coaster itself. We'll just take the default of coaster-petg.gcode. Then we hide the coaster and make the inlay visible. Before we do the export, you'll note that we have a skirt. That's going to get in the way when we combine the two files together. So we'll go into our print settings, skirt and brim, and set the loops to 0. And now we can export the Gcode for the inlay. That's it for the slicer. Now we'll move on to editing. So now we have two objects, the coaster and the inlay, and the two corresponding Gcode files. We could in theory print one file after the other and depend on the Z-hop to avoid any nasty collisions. But really it's a lot cleaner and neater for us if we just merge the two files together and have it come out as one print. Really, Gcode is just a text file containing abbreviated commands to the printer. Because we set the right options in Prusaslicer, we even have comments telling us what each of the commands is doing. So I'm going to edit them using VI, my favorite text editor. You can feel free to use whatever text editor you want. I'm not looking to start a holy editor war here. So we start by loading up the coaster base. And we see several of the commands setting the progress display, turning off the fan, and setting our initial temperatures. Finally, homing the nozzle and then lifting it a bit so we don't burn the bed. Wait for temperature and set units to millimeters. Also set to use absolute coordinates. Next it sets to using absolute distances for extrusion and resets the extrusion distance to 0. Prusaslicer retracts and then resets the E distance to 0 at the end of each layer. This is handy because it means that when we append the Gcode for the inlay, we don't have to do any corrections of extrusion distance at all. A layer is a layer is a layer. So moving to the end of the file, we have a bunch of comments, essentially letting us know the configurations that created the file. That can be useful in many cases, but we really don't need it here, so we're just going to get rid of it. Once we get through all of the comments, we find the M73 command setting the progress bar. We find commands disabling motors, homing the x-axis, turning off heaters, all of the things necessary at the end of a print. But we're not really at the end of our print, so we don't need those either. The last thing in the file that we actually do need is where we retract the filament, reset the extrusion distance to 0, and lift Z. The point after that is where we place the Gcode for the inlay, so delete everything after lifting Z. Now I'll put in a quick comment to indicate that the inlay starts here, just for my own benefit, and read in the inlay Gcode. So now we're looking at the beginning of the inlay Gcode, and we see we're doing all of the usual things to set up for printing. But we don't want any of that to happen because we're already set up for printing, and if we do it again, we're wasting time and potentially causing a collision with the existing print. So we need to get rid of some of this. Let's eliminate the setting of the progress bars, disabling fans, and setting the temperatures. We definitely do not want to home all axes. Who knows what collisions could happen doing that. We don't need to lift the nozzle because the nozzle is already lifted. We don't need to set our coordinates or set our units. We've already reset extrusion distance. We've already set the linear advance. If we rehome Z, we're going to have a collision, so let's not. Next, we see a command with the comment lift nozzle back so we don't burn the build plate. But in fact, that would be lowering the nozzle relative to where it is now and would actually burn the lip of the coaster, so we'll skip that as well. Definitely don't need to disable the fan, so we can just come straight through to the layer change. You'll note that it's for Z 1.6, which is the very bottom of the inlay fitting inside the cutout. But we're not ready to go to Z 1.6 yet, or we'll drill right through the lip of the coaster, so let's get rid of that. Finally, we come to a command to move in X and Y to the first perimeter point of the inlay. We do want to do that. After that, we're restoring Z height for the layer. That's correct to do now because we're positioned over the cutout for the inlay exactly where we want to be. So cut out everything before this. From this point forward, everything should be fine. Any travel moves that might take place will be done using the lift Z parameter, and so it'll hop right over the uncut out parts of the coaster base. The inlay Gcode already has the needed shutdown at the end, and even has a copy of the parameters used to generate the Gcode, which will be virtually identical to those used for the coaster. So now we can just save our combined Gcode, and that's the thing we're going to send to the printer. Since we've messed around with the Gcode manually, it's a good idea to preview what the printer will do just to make sure we haven't accidentally left in anything that'll cause a collision or other problems. Fortunately, Prusaslicer provides a Gcode previewer, so we just go to File, Gcode Preview, and pull it up. Now we can load our combined Gcode, and we're going to go through it and have a look at what will actually happen. On the slider to the right, you'll notice that now the layer heights are all out of order. That makes sense because the Gcode itself prints out a vertical order. Fortunately, that doesn't bother the previewer at all. As you can see, when we pull the slider down to the 5mm line, we see the base of the coaster minus any of the inlay. This will be right where the transition takes place. As we move the slider on the bottom, you'll see an indication of the nozzle position appears along with a readout of the Gcode being processed and which line is currently being processed over on the left. You can also see our comment, Inlay starts. So now we'll go up one layer, which actually takes us back down to 1.6mm in height. Now if you look up towards the top of the readout on the left, we can see again our comment, Inlay starts. You can also see that the nozzle has been moved to a position over where we want the inlay to be printed, so that is correct. Now as we step through the first layer of the inlay Gcode, we can verify that it is in fact printing inside the cutout for the inlay, and whenever necessary, it is hopping over the existing print. All is well. It's notable here that if you print this with Octoprint, the Gcode viewer will get a little confused when it starts printing the inlay. Not to worry, the print will go just fine. Since it doesn't crash or mess up the print, a little confusion over the unusual case where later Gcode goes back and prints lower is forgivable at worst. Another example of proper software design. So now we can print the coaster, but in order to complete it, we need to glue a thin layer of cork to the bottom. I find that polyurethane glue such as the original brown Gorilla Glue works well for this. For purposes of stackability, the cork should be well centered on the bottom and just a little bit smaller than the inner edge of the lip of the coaster. So we're back in CAD to make both a template for cutting out the cork and a gluing guide. Since the inlay, the cutout for the inlay, and other dressing are extraneous to this task, we're going to hide everything, and we're going to unhide the base coaster design. We'll start by selecting the face of the coaster and making a sub-object shape binder from it. This will represent the cork backing on the coaster. So in the data pane, we go to the offset and set it to negative 0.5 millimeters. That should give a good tolerance for stacking. We don't need or want a tight fit. So now to make the template, we just select the sub-object and extrude. It doesn't really have to be very thick to act as a template, but if we extrude it to 3 millimeters, the same as the height of the lip above the surface of the coaster, it can do double duty as a support for when we need to apply weight to cure the glue. Now for a gluing guide, I'm thinking just a thin thing that can slip over the back of the coaster with a cutout where the cork should go. So we'll flip the base over to the bottom, select the bottom and create another sub-object shape binder. Since we're going to want it to slip over the bottom of the coaster, we'll set an offset of 1 millimeter. Now we'll set the position to Z-1 so that we can extrude it upward into the coaster, where we can later do a cut to form a nice fitting socket. Now again we select the shape binder and extrude to 2 millimeters. I want the framework of the guide to be 1 millimeter thick, and 1 millimeter will be cut out by the coaster itself. As we can see, because of the orientation of the object, the extrusion actually needs to be negative 2 millimeters. We can select our extrusion and then select the base and do a Boolean cut. So this gives us a guide that can easily fit over the bottom of the coaster. Now we just need to make the cutout for the cork, so I'll unhide the base again. We'll select the face inside the lip and extrude it to negative 4 millimeters. This isn't a matter of precision, it just needs to protrude far enough to cut completely through the gluing guide. So now we'll select the gluing guide and our extrusion and do a Boolean cut. I haven't provided any tolerance at all since this is a thin, flimsy thing. It'll easily enough snap over the bottom of the coaster without any specific tolerance designed in. This is just the starting point. If you're so inclined, you could do a print with multiple inlays, inserting M600 commands between them to change filament colors. I may do a future video showing an example of that, but for now it's an exercise for the viewer. This technique can be useful even if you have a printer with automatic filament changing. Most of those will change filament colors at each layer and so will purge a lot of extra filament. Even IDEX printers will tend to purge a little bit to deal with the nozzle dribbling while it's idle. Every little bit of plastic we save counts. Eventually slicers might use a technique like this themselves. Thank you for watching. If you liked this video or found it useful, please like, subscribe, and share. If there's anything you'd like to see covered here, please let me know in the comments below.